In this chapter, we're going to study a different type of power cycle. We're going to study power cycles that are vapor power cycles. We've already covered gas power cycles, so now we'll focus on cycles where the working fluid goes back and forth between the vapor phase and the liquid phase. Now, most commonly, vapor power cycles are used in closed systems, and in particular, of course, it's used for power generation for the, probably not the majority, but at least about half or so of the power we use in terms of electrical power comes from burning some type of fuel to generate high pressure steam, which then pushes a turbine. So we need some type of cycle to analyze the actual cycles we're going to have and see what we can do to make them more efficient. We'd like to burn less coal or less natural gas. We'd like to make more electricity per pound of fuel or per kilogram of fuel that is purchased and make the system more efficient. So let's consider the Carnot cycle. Why not? Let's start there. And if the working fluid goes back and forth between the liquid and the vapor phases, then the cycle diagram will have to be superimposed around the vapor dome somehow, because the working fluid goes back and forth between vapor and liquid, and so that's the vapor dome. So if we consider the TS diagram for a Carnot cycle, it's just a rectangle, and so we can superimpose that rectangle on top of a vapor dome. And if we put it where one of the processes is above the vapor dome and the other one from 3 to 4, for example, is below, and then the other two are just vertical, then it kind of makes some sense if you think about it. 1 to 2 needs to be an isothermal heat addition for the Carnot cycle to be valid, right? 2 to 3 needs to be isentropic expansion, 3 to 4 isothermal heat rejection, and then 4 to 1 on the left, isentropic compression. Now, what are all these things, and would the Carnot cycle actually represent this well? Well, actually, if you look at the process from state 2 to state 3, the isentropic expansion, well, we're going to allow the steam, which is on the right-hand side of this vapor dome, we're going to allow that steam to expand in a turbine. Ideally, we want the turbine to operate isentropically, so this process from state 2 to state 3 seems quite reasonable, because the ideal situation would be to have a turbine where the steam is expanding reversibly and adiabatically, and so its entropy remains constant, therefore its temperature is going to drop, giving off energy. So 2 to 3, that's a great model of what we want in our actual cycle. 3 to 4 is the process that's beneath the vapor dome, and it would go from a saturated vapor to a saturated liquid state. Now, that is the constant temperature or isothermal heat rejection process. Now, this makes sense also, since the water vapor, well, not water necessarily, usually we use water, but since the vapor is at the saturated vapor state, as long as we can hold the pressure constant as we remove heat from the working fluid, say in a heat exchanger, well, then all that's going to happen is a phase change. There won't be a temperature change. So we could pretty easily accomplish an essentially isothermal heat rejection process. So far, this is looking pretty good. The Carnot cycle looks very promising. From state 4 to state 1, there's isentropic compression. Notice now we're on the left-hand side, technically in the side where we're in the liquid phase. So getting a pump, and modeling that pump as isentropic is what we would shoot for. That's what we would want a pump to be. The problem comes into the constant temperature heat addition, where we're converting above the critical point from liquid to vapor. That's problematic. Doing that at constant temperature is practically impossible. So there's no way we could maintain constant temperature during heat addition. That would just be too difficult. So this is the one process in the Carnot cycle that means so far the Carnot cycle is not an adequate model for our ideal vapor-liquid power cycles. Okay, well, what if we move the Carnot cycle under the vapor dome instead? Because it's actually not all that common to have processes operate supercritical or above the critical point of the working fluid. It does happen. We'll get into that a little later. But what if we instead just move the Carnot vapor cycle under the vapor dome? And then the process from state 1 to state 2 and the process from state 3 to state 4 both would be just fine. They both would be under the vapor dome, and since we're going from a vapor to a liquid or a liquid to a vapor, as long as we do that under constant pressure, if we're under the vapor dome, the temperature is going to remain constant. So now these two processes look quite practical. Well, it's looking promising. We do want to have isentropic turbines, for example, so the vertical shape of the process from state 2 to state 3, the isentropic expansion looks good. The only problem you might notice is that state 3 ends up sort of, it's still closer to the to the saturated vapor state than it is to the saturated liquid state, but that still represents a relatively high percentage of liquid in the output. Now that's not good for turbine blades. If you know anything about turbines, you know they spin at high RPMs. And if liquid droplets touch the blades at high RPMs, you're not going to have blades very much longer. So the high liquid content or the very low quality steam that's leaving the turbine is problematic for any turbine design. So that process is not necessarily all that practical, so we've got a problem there. Also, to get from state 4 back to state 1, we would need some type of pressure increasing device, something that can deal with both liquids and gases. That's going to be difficult to find. Also, we want to aim for the saturated liquid line, and that is difficult to hit with controls. So this process doesn't adequately model what would go on in the real cycle, because it's just too difficult to accomplish. And so again, the Carnot cycle has failed us. There are two different processes in it that seem reasonable, and depending on whether we were above or below the critical point, some processes seem more practical than the others. So what is a practical cycle model? Well, the ideal Rankine cycle is inspired by the Carnot cycle. And you'll notice that we've just taken the Carnot cycle from the last slide and just moved the expansion process from 3 to 4 and the compression process from 1 to 2 outside of the vapor dome. So what happens here, let's follow it through the system. From state 1 to state 2, the fluid is moving through a pump. And if you look at the TS diagram, you'll notice that the process from state 1 to state 2 is in the compressed liquid region. This is wonderful because all we have to do is buy a pump to pump liquid and increase the pressure of that liquid. That's a problem that's solved. You can buy those off the shelf, no problem. And ideally, you would want this pump to operate isentropically. So the fact that the process from state 1 to state 2 is a vertical line, that's fine. That's exactly what we would want. The process from state 2 to state 3 is a little bit different. You notice before with the Carnot cycle, we simply had state 2 and 3 on the saturated liquid and saturated vapor lines respectively. That's not really practical. So what we're going to do is pump subcooled liquid into a boiler and add heat in that boiler until what leaves the boiler is superheated steam. So the boiler will have to take subcooled liquid water, increase its quality, or in other words its temperature, to the point where it becomes a saturated liquid, boil off all of that liquid by continuing to add thermal energy to it. And even though we get to the point where all the liquid has boiled off, we want to add even more heat to it by burning a fuel to move the steam, because now it would all be steam. We want to move that steam into the superheated region. Why would we do that? Well, the reason is because we want that move through the expansion device from state 3 to state 4. We want that to be farther over to the right. We want to not have a lot of liquid in the exit of the turbine. So from state 3 to state 4, moving through the turbine, a lot of turbines can accept a little bit of liquid in their output, but not much. And so we want state 4, the exit of the turbine, to end up near the saturated vapor line, if not on it, or maybe even slightly superheated, just somewhere in that region, but not much liquid at all coming out of the turbine. So if you look at state 4 on the TS diagram, you'll notice it's just barely inside the vapor dome, and therefore what's coming out of the turbine is primarily vapor, but maybe a few very small liquid droplets. And then from state 4 to state 1, there's a move through the condenser, where the steam comes out of the turbine and is condensed into liquid. And that's pretty easy to accomplish. That constant temperature process is easy to accomplish because the pressure in the condenser is constant, and so the temperature would be constant since there's a vapor-liquid mixture there. And of course, it's pretty easy to make sure that the only thing that comes out of the condenser is saturated liquid. You just need a steam trap, and those are commonly available items. So since the Rankine cycle is being operated with open devices, in other words, devices that have mass flow through them, we have to use an energy balance that accounts for the enthalpy of the flowing stream. And you should become familiar with this and be able to just remember and know that the process from state 1 to state 2, the isentropic compression occurs in a pump. 2 to 3 is constant pressure heat addition in a boiler. 3 to 4 is isentropic expansion in the turbine. And 4 to 1 is constant pressure heat rejection in a condenser. So the equations that will go with these are the work of the pump. Now the pump work would just be equal to, well, I should say the specific pump work is equal to the enthalpy change of the water across the pump. Now the enthalpy of the water coming into the pump would be the enthalpy of saturated liquid, because remember, we're going to put a steam trap on the output of the condenser so that the enthalpy of the stream coming out, well, it's just a saturated liquid stream, so its enthalpy would be the enthalpy of saturated liquid at the condenser pressure, P1. But really, this energy balance is not the only one that we use. In fact, it's not the first go-to energy balance. Instead, the so-called isentropic pump work, when you're trying to increase the pressure at constant specific volume, this is the equation we'll go to. And you may remember this from the chapter 7, I think it was. No, it wasn't chapter 7. It wasn't chapter 5. No, maybe it was chapter 7. Yeah, the isentropic pump work. This is neglecting any kinetic and potential energy changes across the pump, but it is an isentropic equation, and it's the ideal amount of energy that would be required in the pump if the pump was completely isentropic, in other words, adiabatic and reversible. It's the amount of work that the pump would actually need to take a fluid of a particular specific volume, that's what that first V stands for, and increase the pressure from P1 to P2. So this is the equation we'll use most often for the pump in the Rankine cycle. Now you might look at this and say, well, that kind of makes sense. I mean, if the specific volume of the liquid doesn't change as you pressurize it, then it makes sense there would be just one value of the specific volume V in this equation. But where would I get it from? Well, again, remember that the liquid coming out of the condenser is going to be a saturated liquid. Therefore, its properties are the same as the saturation properties of that liquid at the condenser pressure. So to get the specific volume, which will be the same whether it's at state 1 or state 2 essentially, we'll just approximate it as the specific volume of saturated liquid at the condenser pressure P1. From 2 to 3, this is in the boiler, and to analyze what's going on here, one of the equations we'll want is an energy balance to calculate the amount of heat flow in. So this is a specific energy balance. It's the amount of heat that has to be added per unit mass that flows through the boiler in order to increase the enthalpy of that boiler from state 2 to state 3. And then the turbine is the next piece of equipment as the superheated steam moves through the turbine doing work, pushing the blades to do work. And the enthalpy of that steam drops, and in fact some of that steam may liquefy out a little bit. That's what state 4 is showing us. But all we really need here is an energy balance that involves the work output of the turbine and the enthalpy change of the steam. And then for the condenser, even though there's a phase change in the condenser, all we really need is the enthalpy change across the condenser. So understand that at state 4 you've got mainly steam, and state 1 you've got a saturated liquid, and both of these enthalpies would be taken at the condenser pressure. So what lessons can we learn from this about efficiency? Well, unfortunately, if we try to play the game we played with the gas power cycles, it doesn't work real well. Instead, what we usually talk about in terms of efficiency of, say, a power plant, which is where this is most commonly encountered, what we usually talk about is what's called the heat rate. And the heat rate is the number of BTUs of heat required to produce 1 kilowatt hour of electricity. Now, what you really want is to minimize the heat rate. You want to minimize the amount of heat you have to put into the process or this cycle in order to generate a kilowatt hour of energy that you can then sell. So heat rate is sort of like the inverse of thermal efficiency, and in fact there is a conversion. Thermal efficiency is a unitless measure. Heat rate has units. It's BTUs per kilowatt hour, which is kind of strange because it's involving both metric and English units. But essentially it's just a conversion factor because BTUs are a form of energy. Kilowatt hours are also a form of energy. They're just BTUs is usually talking about heat or thermal energy, and kilowatt hours is usually talking about electricity. But they're both energy, right? They both are measuring energy, and so by converting between BTUs and kilowatt hours, you can actually come up with a thermal efficiency. Now, notice that the Rankine cycle is actually fairly close to the Carnot cycle. So this gives us some ideas of what we might be able to do to increase the Rankine cycle efficiency. Remember, the Carnot cycle taught us that the efficiency is 1 minus TL over TH, and while that is not exactly the efficiency of the Rankine cycle, it does suggest some things. So it suggests that if we lower the temperature of the energy that we're throwing away, or if we raise the temperature of the energy where we're getting heat from, well, we could or we should be able to increase the efficiency of the system. And so if you look at a Rankine cycle, what this is saying is that if we could decrease the condenser pressure, well, what would happen? Well, if we condense the condenser pressure, remember the condenser is from state 4 to state 1, we're going to move it down in terms of pressure. That's going to move the temperature down, right? Because the temperature and pressure depend on each other under the vapor dome. So if the pressure is reduced in the condenser, which is something we can do by just running the pump real hard, then the pressure is going to drop. And if the pressure drops, then the temperature at which we're throwing away waste heat will go down, and that's a good thing. So we're going to try to effectively decrease the temperature at which we're throwing away waste thermal energy. One of the problems with this is the increased liquid output in the turbine. If you look at the difference between states 4 and 4' on the right-hand side, you'll notice that 4' ends up at a point where there is a lower quality. In other words, there's more liquid in the output. It's still mainly steam, but there's more liquid in the output, and that can be problematic with our turbine. Also, there's a limit to how far down you can take condensers. You may not know this, but the water that's commonly used in coal-fired plants or natural gas-fired plants, this water is actually very valuable. The water that circulates inside of the loop, driving the turbine and then coming back through the condenser, being pumped back up to the boiler pressure, and then evaporated again, that water, well, let's put it this way. What do you get when you mix steel and water? Well, not much unless there's oxygen present. Well, did you know that water commonly has a decent amount of oxygen dissolved in it? It's the reason fish can breathe underwater, right? What they do is they extract oxygen from the water, not by breaking apart not by breaking apart hydrogen-oxygen bonds, but by getting at the oxygen that is dissolved in the water. Now, that sounds like a recipe for rust in this system, right? What are you going to do? Pay hundreds of millions of dollars for your process and the turbine just to find out a week later it's all rusted and no good? That doesn't work. And so the water that's in these systems, the working fluid, is treated to make sure that there are not dissolved solids in it, which can foul up heat exchangers, to remove as much oxygen from it as possible so that no rust develops on the internal components, and of course to keep it generally clean and in good working order. So going back to the condenser, if we reduce the condenser pressure so far that now the pressure in the condenser is below atmospheric pressure, what happens if a leak develops there? Well, we won't see a leak, right? What would happen is air would leak in because the pressure is so low. Well, if that happens, air is going to get into the process fluid, right, into the working fluid. That means there's going to be oxygen in it. We're going to have a problem pretty quickly because now the whole process will rust up. We can't afford that. So it's not practical to reduce the condenser pressure below atmospheric unless you can be absolutely sure that that air cannot get into that liquid. So there are some problems with decreasing the condenser pressure in order to lower TL. Well, here's another idea. What about if we were to superheat the steam in the boiler even farther? That sounds like a good idea. If you think about the area enclosed in the cycle diagram, you'll notice that all of these ideas so far have increased that area. And even on the TS diagram, the area enclosed represents the amount of work produced. So this is a good thing. We're getting more work out of all these ideas. It's just there are some practical limitations. So if we increase the final temperature and enthalpy of the steam as it goes through the boiler, what would happen? Well, let's see. Essentially what we're doing is we're increasing the temperature at which we're adding thermal energy, right? We're not doing anything about state 2. Notice the temperature goes up until it reaches the saturation line along the process curve, remains at constant temperature as it boils off, and then from the saturated vapor line moves up to either state 3 or state 3 prime. But, so there's not just one temperature at which heat is being added. That's why that reversible efficiency doesn't work, right? The high temperature is not one. There's a multitude of temperatures. But effectively what we're doing is increasing the higher average temperature at which heat is being added to the fluid. So, hearkening back to the Carnot efficiency, this should help increase efficiency because effectively we're increasing TH. Well, that sounds like a good idea, and well, look at this. There's a nice byproduct. We're reducing the liquid in the turbine output. That's good for the turbine, good for our process. What limits it, though, is the blades. Turbine blades move very fast, and so as you heat up metals, they can start to creep. And you don't want to soften the metal to the point where it creeps, because then again we need a new turbine, which is not cheap at all. So about the maximum temperature that just everyday materials can take is about 1,150 degrees Fahrenheit or so. So that's sort of an upper limit on what we could do. Well, what about this instead? What about if we increase the boiler pressure? Well, if we increase the boiler pressure, what's going to happen is that the temperature overall at which thermal energy is added will increase. Notice we went from look at the process from state 2 to state 3 and contrast that with the process from state 2 prime to state 3 prime. Well, from 2 prime to 3 prime, the temperature overall average is a higher temperature, and so we're adding heat. That's the boiler process, remember. We're adding heat at an overall higher average temperature, and this is a good thing. Now, notice we are limited on the upper end by Tmax, the maximum temperature that the turbine blades can actually accommodate. So we'll increase the net amount of work, but there's a drop on the right-hand side because we can't increase the temperature so far. We end up at state 4. We have to end up at state 4 prime. And so there's a trade-off there. The efficiency does rise, but of course, and that's due to the increase in average temperature where we add heat. The problem is that we end up with increased liquid in the turbine output. So it seems like no matter what we do, we're always reaching physical limitations, whether it's atmospheric pressure or material limitations. And of course, new materials could get around these problems. But basically what it means, with a higher pressure, we're going to have to put more metal at it. Right? We'll have to put more metal in the boiler so it doesn't explode, more metal in the turbine because it's dealing with higher pressures. And so we end up with a larger, more costly as far as materials go, system for the same power output essentially. Now that's not really so bad because these installations are most frequently in either extremely large ships where you don't care so much what the weight of it is, or installations on the ground where you're just setting it on concrete. And it doesn't matter. The biggest difficulty here is the increased liquid in the turbine outlet. Well, is there a way to really increase the boiler pressure? Actually, there is. There are some materials, some exotic or semi-exotic materials, that can take much higher temperatures. And if you use those materials to make the turbine may be more expensive, but if it can take the abuse of the high temperature, you can actually run what's called a supercritical process. There are some supercritical plants in operation, even near us here in Louisville, as I recall. I think LG&E operates one. You can look it up. I don't remember. I'll try to look it up and give you a web link. But anyway, a supercritical process is where the pressure is increased so much that as the liquid moves through the boiler, it actually flies above the critical point, and that's why it's called a supercritical process. And of course what happens here is that the overall average temperature at which thermal energy is added is very high. Now this is great. The only problem is that you've got a pretty expensive process there, because number one, you're dealing with not only exotic materials in the turbine in order to deal with the very high temperatures. You also have to have a lot of this material. You have to, super insulate and reinforce the boiler because you're dealing with such high pressures in the boiler. So this is an expensive plant to build. That's the issue. So, but it does increase the average high temperature to increase efficiency. Of course, you have to deal, like I said, with the very high pressure. And there are limitations to what these materials can take, and so one of the trade-offs is the amount of liquid in the exit of the turbine. Well, all of these problems beg for a different solution. Now let's go back to the system where I said, what about if we increase the boiler pressure, but not just ridiculously? Well, if you look at this diagram, you might think, you know, it'd be nice to have kind of the best of both worlds, right? What if we could go from state 1 to state 2 prime, then through the boiler to state 3 prime? If there was some way to get from state 3 prime to state 3, we could go down to state 4 and life would be great. Well, there's actually a way to do that. And it will overcome all of our problems, because think about it. If we could go from 3 prime to 3 and then down to 4, the only real problem we'd have is the increased pressure. But as long as we don't have to use super expensive materials, that's not that much material cost. And it may be a larger system for the same power, but because it's going to be high pressure, but we're setting it on ground anyway. So how could we do this? Well, you can use what's called the ideal reheat Rankine cycle. The idea here is let's break up the turbine into two parts, possibly even having two totally separate turbines. Let's have a high pressure turbine and a low pressure turbine. So what happens, see, is most of the process occurs as normal. Through the condenser, through the pump to get up to the boiler pressure. After the boiler, go into the turbine, and instead of the high pressure turbine going from state 3 prime down to state 4 prime, you only extract a certain amount of energy from the steam. Now let's jump over to the TS diagram on the right hand side and see how this works. So we're going to go from state 3 to state 4 in that right hand side diagram. State 4 now is after the high pressure turbine, and rather than sending this steam to the condenser, let's borrow an idea from the Stirling cycle. Let's use a regenerator. In other words, let's take this, I'm sorry, not a regenerator, pardon me. Let's reheat this. So let's take this steam, and rather than just putting it into the condenser, let's take it back to the boiler through a separate set of piping that's at a lower pressure. Okay? And let's reheat it. Let's put thermal energy back into it. So we'll move from state 4 to state 5 in the boiler through the reheat coils. Now we're at state 5, where we have a fairly high temperature, but still don't need exotic materials, and a fairly high quality steam, so that as that steam expands through the low pressure turbine from state 5 to state 6, now we end up with the output of the low pressure turbine having relatively low amounts of water in it, or liquid water I should say. It still has plenty of gaseous water. We've got all the benefits and none of the problems. The only real problem here is the increased complexity of the high and low pressure turbine, and of course the reheat piping. So the other problem is, of course, controlling that intermediate pressure, which of course you should note that the pressure at states 4, 5, and 5 are the same, whereas the pressures at states 2 and 3 are the same, and it should be obvious the pressure at state 6 and 1 is the same too. So you've got three separate pressures to deal with here. But if you could control this, this would have all the advantages of increasing the boiler pressure, but also still having an exit steam out of the low pressure turbine that the turbine will be able to live with and not be destroyed by. There won't be a bunch of water droplets in it. So this is a good idea. Reheat is actually a really good idea. There's also a cycle called the ideal regenerative Rankine cycle, and this does borrow more from regeneration or the Stirling or Ericsson cycles. But the idea here is that could we somehow reuse the heat? Is there some way to set aside energy to be reused and not just thrown away? Well, notice what happens here. Instead of using the classic TS diagram for the simple ideal Rankine cycle, what we're going to do is add what's called an open feed water heater. The open feed water heater is little more than a mixing chamber. That's all it really is. Now this is a little bit confusing for students to understand at first, but stay with me. So let's start at the exit of the boiler, state 5. And if you look at state 5 on the TS diagram on the right, you'll see it's at the top of the turbine. Okay, so we're going to allow all of the steam to expand in the turbine from state 5 to state 6. Now state 6 is not the condenser pressure. It's an intermediate pressure between the high pressure of the boiler and the low pressure of the condenser. And what are we going to do at that point? Well, we have to have a tap on the side of the turbine where maybe the steam has gone through a few sets of blades, but now we allow some of that steam to bleed off. It's called bleed steam. So you bleed the turbine. Now, a fraction of the steam is allowed to exit the turbine at this point at an intermediate pressure and not complete the journey through the turbine, expanding all the way. The rest of the steam, though, does move from state 6 to state 7. So there's a split at state 6, okay? State 6 is a state that all of the steam experiences. Some of it experiences it, well, it all experiences it in the turbine. Some of it then bleeds off and leaves. The rest of it continues moving through the turbine, state 6 to state 7, goes through the remaining blades in the turbine, expanding and pushing those blades doing work. So let's follow the steam that remained in the turbine and that goes through the condenser. Well, all of the energy that remains in that steam will have to be thrown away. That's the waste heat. Then we'll go through pump 1. Now, pump 1, the process from state 1 to state 2, brings all of that condensate up to the intermediate pressure, not the boiler pressure, but the intermediate pressure of the bleed steam that just bypassed the whole condenser pump 1 part. Okay? It just took a shortcut, right? Took the exit ramp out of the turbine and went right into the open feed water heater. So stream 6, or state 6 and state 2, those two streams have the exact same pressure, you see. And so then what happens is those two streams just mix together. Now, think about it with me for a moment. Look at the TS diagram, look at state 6. State 6 is still superheated steam. Well, that superheated steam is mixing with what? It's mixing with saturated, well, actually subcooled liquid coming out of state 2. So look at state 2 and look at state 6 on that diagram. When those two streams mix together in the open feed water heater, which is just a mixing chamber, they come out at state 3. Now, this is really important because look what's happened. Where originally did the boiler have to add heat at the lowest temperature? Well, coming out of the pump, right? Whatever's coming out of the pump is the lowest temperature. Look what we've done here with this open feed water heater and bleeding steam. We have completely eliminated the lowest portion, the lowest temperature portion of the heat addition that the boiler had to take before. This is a really good idea. From state 2 to state 3, that move is accomplished by simply mixing the bleed steam in with it. And we end up, if we control this right, we can make state 3 end up on the saturated liquid line, maximizing the effectiveness of the bleed steam in raising the temperature of what's coming out of pump 1, stream 2, or state 2. So we end up at state 3. Look at the TS diagram, and from state 3 to state 4, we're moving through pump number 2 to go from the intermediate pressure up to the boiler pressure. And then finally continuing through the boiler, the cycle repeats. The reason this increases the efficiency of the Rankine cycle is that we don't have to add heat to the water, the liquid, subcooled liquid water, at really low temperature. So we're, again, increasing the average temperature at which thermal energy is flowing into the cycle. So that increases the, as I just said, increases the average temperature at which we add heat. Now, the cost for this is the fact that we've got to have a bleed tap on the turbine. The cost to you as a student is that this starts to get really confusing because students look at that Y and they wonder, why is it there? What's that Y for? Well, remember, not all of the steam goes this way, right? Most of the steam usually stays in the turbine and expands all the way. It's just some bleed steam that's pulled off of the turbine in order to preheat the water coming out of state 2. Now, students get all confused about this because most of the time up to this point, we've had just one mass flow rate through the whole system. If it went through the boiler, it's going to go through the turbine, right? If it went through the turbine, it's going to go through the compressor. Same mass flow rate through the entire system. Now we're bending that, right? We're changing that a little bit. And so now we have to keep track of what's called the mass fraction. Don't worry about the name mass fraction. It's just a percentage, nothing more, nothing less. It's just what percentage of it goes the other way. So Y, for example, if Y was 20%, what that means is that 20% of the mass that comes through state 5 goes into state 6. The other 80% goes into state 7 after going through the turbine and finishing its expansion. So if you look at the labels, are pretty small, but there's a Y by state 6 and there's a 1 minus Y by state 7. That should make sense now, right? Because if Y is 20%, then 1 minus 20% is 80%. And it's nothing more or less than this. The only thing to realize beyond what I've told you is that the largest mass flow rate in the system would be stream 4 and stream 5, because that's all of the mass moving through the boiler. The mass kind of diverges at the turbine and then recombines at the open feed water heater. So really the mass flow rate at state 3, 4, and 5 would be the highest. We usually talk about the mass flow rate through the boiler because all the mass does have to go through the boiler. So the fraction can be calculated as the mass flow rate that goes through state 6, the bleed steam flow rate, divided by the mass flow rate through the boiler, or state 5. So this is how we define it, and it's something that we have to keep track of. I've got some handy equations here for you. Since not all of the steam fully expands in the turbine, the specific work in the turbine is a little bit confusing to calculate. Remember, usually our relationship between work power output and specific work is that work power output equals the mass flow rate through the turbine times the specific work. That doesn't work here because not all of the mass goes through the turbine. That works for the first drop from state 5 to state 6, and so you see H5 minus H6 as the first term in the specific work produced by the turbine. But we have to take 1 minus Y, in other words, only 80% of the mass flow rate, times the second drop from the intermediate pressure to the condenser pressure, state 6 to state 7. That's why there's 1 minus Y times H6 minus H7. So what you'll want to do is find all of these cycles in your book. Make sure you've got them tabbed, and especially around the regenerative Rankine cycle, you want to write down the equations I've got on this slide. They'll be very handy for you. Similarly, not all of the steam goes through the condenser, right? Only a fraction of it does, 1 minus Y fraction. And so the specific heat transfer out is 1 minus Y times H7 minus H1. That way we can still use our equation that says Q dot out equals the mass flow rate times little q out. And what mass flow rate are we going to use in all these? We'll always use the mass flow rate through the boiler. Be careful about that. If you want to calculate the power output of the turbine, multiply this specific work by the mass flow rate through the boiler. If you want to calculate the rate of heat transfer out of the condenser, multiply this specific heat transfer, Q out, by this equation by the mass flow rate through the boiler, and that 1 minus Y will take care of the fact that actually not all of the mass through the boiler, or stream 5, goes through the condenser. For the first pump, if we talk about the specific work in that pump, you might think it's just V1 delta P. You use a similar equation for pump 2, but you have to be careful because, again, not all of the mass goes through pump 1, whereas all of the mass does pass through pump 2. So there's a 1 minus Y multiplier by the specific work for pump 1, whereas there isn't for pump 2. And so the total pump work in, you see there I have calculated for you 1 minus Y times the specific work for pump 1, which is V delta P for pump 1, plus V delta P for pump 2. The boiler is pretty simple. Qn is just H5 minus H4. If we look at an energy balance there, that's because to calculate Q dot N, you would simply multiply M dot 5 by H5 minus H4. The regenerative Rankine cycle is a little bit more difficult to understand. With the regenerative Rankine cycle, the idea is let's use not just an open feed water heater, but let's use a closed feed water heater. Well, what is that? Well, if you look, there's just one more piece of equipment. We have 2 pumps. You can see the bleed steam on the turbine, and you can see what's labeled as a closed feed water heater, and then the mixing chamber that before we were using as an open feed water heater. But of course, now we don't have the bleed steam coming straight into it. So now technically it is just a mixing chamber. Well, with a closed feed water heater, how would you do that? Well, you'd simply use a heat exchanger, because what happens is those 2 streams from 2 to 9 and from 7 to 3, they don't mix, okay? What happens instead is this is just a heat exchanger with 2 streams running through it, transferring heat between the 2. Notice that this is really not much more complicated than the open feed water heater in that we still need bleed steam from the turbine. We still have 2 pumps. It's just that now we have a heat exchanger, which is a little more expensive than a mixing chamber, which we still require as well. But let's try to wrap our heads around how this would work. All right, so let's start again at the turbine, which is now entrance state 6. So all of the steam expands in the turbine to state 7, and then some of it, a Y fraction, goes through state 7. The 1 minus Y fraction goes through stream 8, or state 8. Now, if we follow state 8 around, you'll see that it goes through a condenser. Follow it on the TS diagram. Now we have a saturated liquid at state 1, which can then be pumped up to, and it turns out that this pump 1 now, instead of going to the intermediate turbine pressure at state 7, it actually goes all the way up to the boiler pressure. So stream 2 is at the boiler pressure. Okay, it's at a higher pressure than stream 7. Stream 7 coming out of the turbine is a higher temperature but lower pressure stream than stream 2. Now, stream 7 being at a higher temperature will raise the temperature of stream 2 in the heat exchanger, so that at state 9, stream 2 has gone to a higher temperature. Now, of course, in the process, we would want to put a trap at state 3 so that steam doesn't come into the trap. We only want saturated liquid to come out, because if steam escapes through state 3, not only will that mess up pump 2, but that steam represents thermal energy that could have been given up, right? Because if that steam condenses out, it will give up more energy, and that's what we want. We want to put as much energy as we can into stream 2 to take it to stream 9 or to state 9. Okay? So it's a little bit confusing to understand what's going on here, and I have zoomed in. You see the inset up there to explain what's going on here. Let's try to follow this through, and then we'll try to understand the gory details around states 9, 5, 4, and 3. So if stream 9 is warmer than state 2, that means that we don't have to add heat at such a low temperature. Look at state 2 on the TS diagram. See how low it is? If state 9 is higher, look at all that low temperature section we've completely eliminated, where we don't actually have to add heat from an external source. This should increase the efficiency of the cycle. And then if pump 2 takes the stream from state 3, which is at an intermediate pressure between the high pressure of the boiler and the low pressure of the condenser, pump 2 then pumps it on up to the boiler pressure so that streams 4 and 9 can be combined into state 5 and continue through the boiler. So stream 7, the bleed steam, goes to stream 3. That makes sense. Stream 3 is a saturated liquid, and then up through, let's see, pump 2. So 3 to 4 is pump 2, which pumps up to the boiler pressure from the intermediate bleed steam pressure. On the other hand, stream 1 down here goes through pump 1 up to the boiler pressure. That's this whole line is the boiler pressure line. It's all one pressure. And stream 2 goes to stream 9, increasing temperature. This is great. We don't have to add heat from an external source to increase the quality or the temperature of stream 2 to stream 9. We've cut off the lowest temperature portion of that curve where we had to add heat before. So this should increase the efficiency of the overall cycle. So where are we left? Well, we're at state 9 here and state 4. Now what's happening here? Well, let's transition to this diagram. So we're at state 9 and state 4. In the mixing chamber, what actually happens is state 9 is increased to state 5, the exit, and state 4 is decreased to state 5. You see, it can be a little bit confusing following these diagrams around, because you look at these arrows and they only point in one direction. But on this curve, there's something special that happens right in this section. State 2 goes to state 9 here, state 3 goes up to state 4. You might have guessed that. And you might have guessed also that state 9 goes up to state 5, but state 4 actually goes down to state 5. And so what happens is state 5 then is the lowest temperature that the boiler has to deal with in order to add thermal energy. In other words, our external source has to deal with an average temperature on the high side from 5 to 6. Now look at all of the low temperature section we were able to eliminate from state 2 all the way up to state 5. The boiler doesn't see that. The external heat addition does not see any of that. And what that does is increase the overall efficiency of the cycle. Now the cost, of course, is more complication. We have to have a more expensive device than a mixing chamber. We need a heat exchanger. That's more expensive. It's also more expensive to maintain. But we could do this. Now you look at this and you might say, well, this really doesn't give us a whole lot of benefit over the open Feedwater heater. And you'd be right, because it really doesn't raise the average temperature much by comparison to the other for the extra cost. Why on earth would we do this? Well, there's actually a good reason, despite the fact that there's no real benefit versus an open Feedwater heater. The idea is that we could actually include multiple closed Feedwater heaters and multiple bleed streams from the turbine in order to make an overall more efficient system. Steam traps are pretty cheap. Pumps are relatively expensive and harder to maintain, but closed Feedwater heaters, which are essentially just heat exchangers, are relatively simple to maintain and relatively inexpensive to the pumps. So if we could get away with 2 pumps, have multiple closed feed water heaters, we could continuously increase the overall efficiency by cutting off more and more of that low temperature section where we were originally adding heat in the boiler. Now, this is a fairly complicated system, but notice that it doesn't use any exotic materials. The cost increase is there, but we're going to get more money out of our coal that we burn, because we've got to burn less coal now to generate the same power, because we've got a more efficient system. Controlling this is not all that difficult. All you really need is a steam trap in order to make sure that there's only liquid leaving each of the closed feed water heater heat exchangers. In other words, making sure that the bleed steam gives up as much energy as possible. And so yes, it's more complicated. Yes, it requires more complicated controls, but there's a good opportunity for higher and increased efficiency over just a simple Rankine cycle.